So the first talk this afternoon will be by Manuel Gonzalez, and the title is on the quadratic form associated with the purpose of automorphism and its applications to singularity theory.
Thank you very much for the introduction, and I want to say also thank you very much for the organizers of this meeting for giving me the opportunity to be here and to give this talk. Okay, so a word of apology. My topic of my talk is a little bit of topic instead of the conference, but so this is a work with a group of people. Ilia Lanis from Monterrey, Enrique Bartolo from Zaragoza, Cristian Monati from Dijon, Javier Gomez Mon from Guanajuato, and Pablo Portilla from Lille. But Pablo was in Guanajuato at the time of maybe. And the talk is based in a paper that already appeared in Indagaciones last year. Okay, so this is the outline of my talk. Let me speak a little bit about pseudo-periodic automorphisms of the surface first. So we're going to work with sigma, a real-oriented surface of genus G with R certainly bigger than 0 boundary coupling. So the boundary is not empty. And we're going to consider the mating class group of surface diffeomorphisms of surfaces of genus G and with R boundary components with respect to the identity on the boundary components, and this is up to an isotopy fixing the boundary. So just as notation, sometimes I'm going to use phi for a representative of a class in the mapping class. Okay. So this is an example, a very basic example, but it's going to play a role in the talk. So let's consider an annulus, and we're going to consider an automorphism that is called a right-handed end twist of the annulus. So it's of this bond, it's a composition of the inverse of theta with D and with eta. And here, eta is going to be a parametrization of the annulus from S1 times the interval minus one half. And D is given, so this is given by, so it's in two variables, xt, so it's given by x plus t, comma t, and this is after identifying the circle with the real small data. And this is a picture of how this automorphism looks like. So what you see, the green curve just goes around the red circle once. Okay. And so in this case, the mapping class group is isomorphic to the integers and is generated by the class of H, the class of the right-handed entities. Okay. So there is a classification due to Nielsen and Carson that it says that one of the following exclusive statement is false. So the first statement is that the automorphism is periodic. The second that is pseudo and so. So I'm not gonna explain what does it mean because we're not gonna use it. And the third is that it's reducible. So that means there is a representative and a finite union of disjoint simple closed curves that are invariant under this representative. And then what you do is that then you consider the complement of these curves and apply again this statement. And in this way you classify this surface automorphism. And so we are going to deal with pseudo-periodic mapping class groups. This is when you use this machinery and you only end up with periodic pieces. So no pseudo anisotropy. Okay, so maybe a picture. So maybe you can have something like this. Maybe, for example, have here two pieces. I don't know, something like this. Maybe here you have some genus, and maybe, for example, this curve. Maybe you can imagine that there is a curve here and a curve here, and then you have here a periodic piece that attaches these two components of the complement of the curves, and maybe this is a piece that has an automatic order or whatever. Okay. Also, in this theory, you can have a canonical class for an automorphism. So what it says is that there is a collection of simple closed curves C in the surface, and tubular neighborhoods of these curves. The tubular neighborhood is denoted by T, and a representative such that the multi-curve and the multi-annulus are invariants by this representative phi. The restriction of the representative to the complement of the multi-annulus is periodic. And then there is an integer E such that the E power of the representative is a composition of non-trivial powers of right-handed twists along the curves in the collection C. So this minimal subcollection of curves C is called are known as separating curves. Okay, and sometimes you associate a graph with an automorphism. It's called the Nielsen-Clarkson graph, a pseudo-periodic automorphism. And well, essentially, this is how you draw the graph, right? So the nodes corresponds to the periodic pieces, and the edges. So an edge between two nodes corresponds to a separating curve that is adjacent to the two pieces. Okay, so in my data, I say that this is related to singularity theory, and so here I wanted to explain a little bit the relation. So let's consider a germ of an isolated complex surface singularity. So germ of a normal complex surface singularity, and I consider a germ of a reducible morphic map from X to C. Then we have this Milnor left vibration theorem that was already mentioned, at least in the talk by Laurenti Maxime. It says that you have small numbers, epsilon and delta, which is small with respect to epsilon, and then you have a ball V epsilon, such that if you restrict well, I mean, with this epsilon and this delta, you can construct a locally trivial vibration over the boundary of the disk of radius delta, and well, the source of the map is this intercession that written in the slide. Okay. Well, with the locally trivial vibration, there is a fiber F associated to it, which is the preimage of a point in the boundary of the disk. And this happens to be a real oriented surface with the non-empty boundary, what we call the Milnor fiber of F at the origin. And we also have an automorphism of F that is induced by F, it should be F tilde. Okay. And well, we call geometric monodromy, or I just put monodromy to the class of this automorphism. And it's known to be pseudo-periodic. And there is this theorem by Ambition that says that the properties of the canonical class with this integer E bigger than 0, this completely characterize the monodromies associated to reduce holomorphic map germs defined on isolated complex surface singularity. Okay. Okay, so I need to introduce a few other things. So I'm going to introduce these Q numbers. So this is gonna, well, this is a number that you associate to the annulus that are produced by that appear in the definition of the canonical class. Okay? So we are going to have an orbit of separating curves. So that means that when you have these separating curves and you apply, you pick one of them, you apply the automorphism, and it's going to be an orbit. After a few iterations, it comes to the same, right? So this is my orbit here, and this delta is going to be the minimum power of H that sends C1 to C1 with the same orientation. It can happen that the first time that you come back to C1 is oriented in the other way. So then you do, you keep doing iterations until it comes with the same orientation. And let's call M1 and M2 the periods of H restricted to the pieces on each side of this orbit. And let's take the lowest common multiple of these numbers. Call it N. And so what we know is that H to the power N restricted to the tubular neighborhood of C1 is L right-handed then twists around C1. And with this information, we define the skew number of H at the orbit C, and it's just the quotient of delta times C over N. Okay, so here comes the quadratic form that was in the title of my talk. So let's consider the homology operator on the first relative homology group of the surface relative to the boundary. And well, we have canonical decomposition into a semi-simple and unipotent part. And usually, a unipotent and semi-simple part, and usually one can introduce different nilpotent operators with H star. Usually, in the literature, you find these three operators, right? In the case of the isolated plane curve singularities, they consent. So this is just a remark, and maybe to motivate the definition. So now we define N, which is we iterate E times the monodromy operator and subtract the identity. And this goes from the relative group to the absolute homology group. This is again an nilpotent operator. Okay, and then of course we have an intercession product. And so we're going to combine N and the intercession product to define the quadratic form Q, right? So what we do is we pick two classes in the relative homology group. We apply N to one of the classes, and then we do the intercession product with the other class. So that gives us an integer, and also we can mod out the care of the nilpotent operator to have this Q tilde. Okay, so this the thing here is these ones are purely topological, and they are symmetric. Okay, so let me now state the main results. So the first statement says that if the skew numbers are positive, then the bilinear form Q tilde. So this is the bilinear form after modding out the kernel of N, is positive definite. The second statement is that the restriction of Q tilde to the absolute homology is even if the quotient of the Nielsen-Thorson graph on the action of the used automorphism H is at 3. And okay, so what happens to this statement if you consider the case of germs on isolated surface singularities. Okay, so then the screw numbers are always positive. So then in the singularity theory case, the form theta q is going to be positive definite. And the hypothesis on the corollary, so that the quotient of the Nielsen-Carson graph is a 3, false in the case X is a fine 3. Okay. Well, this is also a remark. So this operator n is related to the variation operation. So indeed, it's a variation operation for a power of H, for the E power of H. And then you have this expression there on the right that relates to the powers of the relative homology and the usual variation operation. And also one has the cipher form that I'm not gonna, well, I mean, the cipher form is the link of two classes, and you have to do the push off of one of them, but I don't want to go into the details there. This cipher form is related to the variation operation, and the conclusion of this relation is that the Gaussians I introduced are determined by the cipher. However, so one may ask, well, are you saying something new, or so the thing is that well, hopefully the statement is the statement I showed, or the statements I showed in the previous slide are new. But anyway, this tilde q is computationally much simpler than L, right? So we will see that at the end on some. Okay. So I want to give a sketch of the proof of the results of the result that says that Q is positive. Okay, so the first element in the proof is this lemma that tells you what happened after a dentist. So here we're gonna fix an annulus in an orbit of annuli. Let's say we have D of them, and we are gonna have two properly embedded disjoint-oriented arcs on T, right? So the picture is. And we have E, and we have E. And now this, well, they have orientation. They can be the same or opposite or whatever. And we're going to consider the core curve of T, situated oriented. And we're going to take a number E such that the restriction of the E power of H to the boundary of the annulus is identical. Okay, then what it says is that if I apply the operator n to one of these properly embedded arcs, where I get is a multiple of the core curve, and this multiple has to do with the skew numbers. And the second statement says, well, what sign? I mean, what happens if I do the intercession product with another properly embedded arc from one of the boundary components to the others? And so I get the coefficient that comes with the curve in the first identity, and then I get a sign, and the sign is plus or minus depending on whether the two properly embedded arcs agree on orientation or not. So here I'm going to show you. So this is a picture, right? So what I do here is I apply the dead twist to the red properly embedded arc, and then I have two others with different. E minus 1 has opposite orientation, and E plus 2 has agrees on the orientation with the red one, right? And then And then on the right, I put the red curve is n applied to the red properly embedded arc. And if you look carefully, you can see why the sign comes in the identities above. Okay. Okay. So so this is the lemma that we're going to use to compute this Q. Okay. So first, I'm gonna try to explain why is positive semi-defined definite. And here the strategy is just to reduce the computation to what happened in the orbit of annuli, and then apply the lemma that I just showed. So let's say this gamma B is a collection of disjoint-oriented simple closed curves and properly embedded arcs representing a class of the relative homology group. Let's assume that gamma sub B and the orbit or the collection of separating curves intersect transversally, and all the intersection points of the image under the e power of h of gamma B and gamma B occur in a small neighborhood of the separated curves. Okay, so just let's think about the curves that are intersected by gamma B and are not null homologous. Let's take a tubular neighborhood of those curves. So these are annuli. And so in each of these annuli, what you're going to see is a collection of intervals, and some of them have one orientation and the other. So let's say you're going to have, okay, let me see. Yeah, so this is I'm going to have, let's say, E plus with one orientation, and then I have E minus with another orientation, and I'm going to call it A, E plus E minus. So, but I have to do that for each angle, right? So this is, and then what I do is I apply the previous level. So I'm going to have a multiple SI of the curve CI. And so this is how the computation looks. So if I apply n, I get the multiple of the curve CI, and now I do the intersection product, and I get something like SI times P plus minus P minus if the orientation is positive, and the other identity if the orientation is negative. So I have to sum up this over all the intersecting separating curves. And what I have to do is just manipulate a little bit these expressions that happen here. And actually what I do is here in the bottom line, in the second summon, I'm gonna put the minus outside. And what I get is a multiple of square. So it has to be positive, right? Or not negative, okay? So this at the end, yeah, sorry, it's a lot of notation, but at the end, the conclusion is that Q is positive semi-definite. And so all the summons are like those on the bottom line. Okay, and then final step is to check that it has to be positive. Okay. So what I have to show is that if Q B comma B is 0, then B belongs to the kernel of the nilpotent operator. right? So Q tilde is positive definite if the condition below the equivalence below false. Okay. And so what happens if Q B comma B is 0? What happens is that I have the same number of segments going from one border to the other than the other way around. And if this happens, then the image of the segment by n is 0 in homology, and that thing has to belong to the curve. Okay, so this is about the main result. And okay, so now I would like to discuss a little bit more the case of singularity theory and explain a little bit more how we do some computations. And okay, so now I'm gonna think that I have a germ of an holomorphic map or defined on an okay, so maybe I don't want the word plane here, right? So it's just an holomorphic germ on X that is an isolated singularity. Okay, I'm gonna use an embedded resolution or a log resolution. T, and the total transform of F is a non-reduced normal crossing divisor, and I'm gonna consider its dual graph. And I'm going to consider some decorations on the dual graph. So these are going to be the multiplicity, which is the order of vanishing of the pullback of F by the resolution along the components of the sectional divisor, or the components of the total transform, if you want, and then the genus of these components. So in the case X is the affine plane, well, the genus is going to be always 0, so I'm not going to write it. But okay. Okay, so here a tubular neighborhood of orbit of separating curves corresponds to a bamboo of divisors in the resolution graph. So a bamboo is just a change of divisors valency. Something like this, right? Okay, and in this case, there is a formula which is called the twist formula. So this is a formula that has appeared different times in the literature, and it allows to compute the discrete number around the orbit, right? And so it's computed in terms of the multiplicity, and so this is a justification of why of the positivity of the screw numbers in this case, right? Because here the multiplicities, the decorations of the nodes of the dual graph, these mi's are positive, and then you can see in this formula the screw number. Okay. Yeah, this formula. So I think I at least know 4 places where it appeared in a paper of Dubois, Michel, then a paper of Walter Neumann, and then in the book of CTC Wall, and also my co-author Pablo Portilla gave a proof in his PhD thesis. A different proof. Okay. So I'm going to consider also the semi-stable reduction. So this is a function f super e, which is defined in this commutative diagram. So here, what you consider is, again, you consider the number e. So this is I say before, is the smallest number such that the e power of h is a composition of right-handed then twist. around some simple closed curves. And you make a sigma, a base change, and then you make a fiber product, X super E. And so in principle, this is a B manifold, and then you take the normalization. And this semistable reduction is the map that goes from the normalization tilde X super E to the list, to the bunch-of list of the radius E root of delta. Okay, so one of the advantages of considering the semistable reduction instead of the log resolution is that the total transform is now a reduced normal crossing divisor. So no multiplicities, right? But now in general, even in the plane case, you expect the irreducible components of the total transform to have positive values. And I'm going to denote sigma SS the dual graph. Okay, so this the dual graph of the semistable reduction is a better picture of the topology of the Milnor fiber and of the monodromy than the dual graph of the better resolution. And this can be expressed saying that the dual graph of the semistable reduction and the Nielsen-Clarkson graph associated to H have the same normotopy. Well, this is just a reminder how to construct the dual graph of a divisor and the Nielsen-Clarkson graph that I said before. So the dual graph is going to have a node for its irreducible component, and FGS corresponds to intersection. Okay, so with these things, you obtain a lot of information from the Jordan form of the monodromy of well, again, I don't think I need plane. Here is an explanation. So in the case of plane curves, or more general, in the case of homology spheres, right? So fiber links with fiber F in a three-dimensional homology sphere whose complement is a graph map. So this is a situation that appears many times when you study these isolated singularities. So in these cases, you can express the characteristic polynomial of the homology in the H1 of the fiber, or the characteristic polynomial of H1 of the fiber mode the kernel of M in terms of the dual graphs and their decorations, right? So you have expressions like this. Well, the details are not important, right? But you have to consider the set of nodes, the set of edges, and their multiplicities, and okay, the delta is the earlier characteristic. So the genus minus the valence. Okay, so in particular, the number of Jordan blocks, which are of, which in this case we know, we will later see something are of size 2, is given by the first Betty number of the dual graph of the semistable relative. Okay. So this is a couple of examples. So the first example of a Jordan block of the monodromy for plane curves is due to Acampo, where he considers is what is called a Loeber curve. So he considered Acampo gave this example. So it's 3-2 curves with perpendicular tangent forms, right? So here we consider, instead of 3-2, we consider 7-6 to produce more Jordan blocks, right? But so this is so in this case, the rank of the rank of the first homology group of the Milnor fiber is 131. So this is gonna be the degree of delta t, which is the characteristic polynomial of the monodromy, and delta 2 gives you the Jordan blocks. So it's telling you that there are 5 Jordan blocks. This is another example, right? So it's based on the same idea. So it's the equation. So it has 2 components: the equation, which are 2 irreducible curves, but with 2 characteristics, and the tangent constant perpendicular. And well, right. So I didn't say before. The graph on the top is the resolution graph. The second graph is a retraction of the dual graph of the semistable relation. Okay. Okay. So here, so we did a lot of computations. I will show you later on computations of Q. So what we do is we explain how to compute tilde Q or Q on the dual graph of the semistable relation, right? So we consider the first homology group of the dual graph of the semistable relation relative to D, which are the arrows. These arrows correspond to boundary conditions. Okay. So now we're gonna consider the collection of separating cars C, but we have to consider also the boundary components of the Milnor fiber. And this is what I call calligraphic C plot. Okay. I'm gonna take a tubular neighborhood of called C plus in A, and F sub C is gonna be the close complement of the tubular neighborhood. So I'm gonna consider the log sequence of the pair F, comma F sub C, and I'm gonna use the System formula to identify the relative groups with homology groups in rank 1 unit less of C, and then I get this is the longness at C. So from this log sequence, you can deduce the monodromy theorem that tells you that the monodromy is a quasi-nicotent. So the eigenvalues are root of the unity, and the size of the Jordan blocks is almost. But well, this is just a side remark. Also, one can consider with this sequence an increased weight filtration. So W0 is going to be the image of the rank 1 homology group of C plus in H1 of the fiber. W1 is the image of the complement, the close complement of the tubular neighborhood of C plus in the homology of the fiber, and W2 is the first homology group of the fiber. So by the twist formula, we can deduce that W1 is the kernel of the M prime, and also you can identify the first homology group of F relative to the close complement of the tubular neighborhood of P plus with the one change in the semi-stable graph, or with the first group of the first homology group of the semi-stable graph relative to the okay. This should be I put the D in the slide before. So this should be the arrows. Okay. A0 of the closed complement is identified with the T0 of the semi-stable regression graph, and we also have an identification of the map from the relative group, the first relative group, to the zero group, zero homology group of FC. So this is identified with the first chain operator of the chain complex of the semi-stable, of the dual graph of the semi-stable relation. Okay. So this is again the log sequence with the identifications, and so we got this isomorphism between H1 of the fiber mod the kernel of M prime with the H1, the first homology group of the dual graph of the semi-stable. Okay, if you want to look at the relative homology group, then you have to consider the homology, the first homology group of the dual graph relative to the arrows. Right. Sorry, I changed again. Okay, so the conclusion of all this is that tilde Q is defined on this problem. And this is what we use to compute it, right? So for example, this is the example I showed you before. So if you look to the second graph, you can see that you have 5 independent absolute cycles, and then you have another cycle that goes from one arrow to the other arrow. So Q tilde is defined on it represented by a matrix of size 6, and this is the matrix that you have there. So the 5 times 5 top left box corresponds to the absolute cycles, and the other corresponds to a path that goes from one arrow. Okay. If you want to know more details about the computation, you can check the paper. But I want to mention two examples that are very well known in singularity theory for historical reasons. So first is this example of Timbrick, Stevens, and Schrauben. So this is an example of 2 pairs of cars with 6 components. You can see 6 arrows in the diagram that have the same spectral pairs, but the topological type of the cars is different. Okay, so this is really a family dependent on K, L, M, and N, but I just made the choices that are written down on the slide. And so the pictures, the top pictures are the resolution, dual resolution graphs for the 2 curves, and then you have the dual graphs of the semi-stable relations. And so I'm not going to show you the matrices here because they are very big. But when we compute this, that the matrices corresponding to Q tilde have different determinants, even up to the square. So that tells you that in this case, tilde Q distinguishes these two different topological types. Okay. The second example is this example due to Dubois-Michel. So this is an example of showing that so 2 cars again with different topological type, but the same cycle. So here the thing is that again, this is a family depending on some parameters A, B, and A, B, and then A, B depend on alpha and beta and so on. and you have some conditions, right, and some symmetries. But and there's some conditions that are written down there. You produce an example of the two topological types with the same cipher. Okay, so here the rank of the first homology group of the Milnor fiber can be as big as you want. Because it's given by A plus B plus 73. And you can pick A and B as large as you want. But in this case, the rank of the first homology group of the dual graph of the semistable relation is fixed. So here, this is why I said before that this is computational much simpler than the cipher, right? So you are looking only, in this case, it's rank 5, right? My matrix is rank 5 or 4. This one. Okay, so in this case, what we see is that so we compute the matrix. It has this form there, so it's a little bit complicated. It depends on these parameters I and B. But the thing is that if we compute for the two examples, we get two matrices that have this symmetry here, right? So essentially, we are not able to distinguish them with the feedback. Okay, so this is the last example. So this is not a plane card. So this is defined on a germ of an isolated surface singularity, which is given by this equation there. Okay, so this is an Eicher surface in C3. Actually, it's an example of what is known in singularity theory as a super isolated singularity. That's not important for the purpose. Okay, and I'm going to consider F given by a generic linear form. Okay, so in this case, the Milnor fiber we get is it has the topology of a torus minus 3 points or 3 digs, and the monodromy is a composition of them twists around 4 curves that are drawn in red in the picture. So actually, the picture shows you also the E1, E2, E3 are a basis of the relative homology of the Milnor fiber. On the left and on the right is after you apply the monodromy. So you see that the blue curve makes them twist around the red ones. Okay, so in this case, Q tilde is the matrix below, and in this case you can see that it's not even. So this example wants to illustrate that we are able also to do computations in the non-plane case, but also that the hypothesis for the hypothesis that the quotient of the Intercession graph under the monodromy is a tree is really sharp, right? So once you don't have this, you can find examples like this one where the tilde Q is not in. Okay, and also we use the computer to do some of these computations and more, and these are available if you want to see them. And that's everything I have to say. So thank you very much.